Find the acceleration of rod A and wedge B in the arrangement shown below. The ratio of the masses is given to phi, or whatever Greek letter that is, and the friction between all contact surfaces is negligible. As you can see, rod A is constrained to move downward, only downward. And the implication of A, the rod moving only downward, is that the wedge move only rightward. So the wedge move only in the x-axis to the right, and the rod moves only in the y-axis down. The key in this problem is to find the constraint equation. And usually I like to find a constraint equation on the position of the object, and then take a second derivative of that constraint equation and get the constraint equations using the accelerations, because it's what is being asked. Let's do it. In this problem, we need to find the acceleration of rod A and wedge B in the arrangement shown. So as you can see, rod A is constrained to move down, and rod B is then constrained to move right. And the only thing that is given is that the wedge mass is rho times wedge B. So instead of A and B, I will use 1 and 2. And M2 over M1 is 5, or whatever Greek letter that is. And we need to find A1 and A2. So when rod A moves down, it's obvious that rod A moved down this delta y, and we put a y1 because 1 is the rod and 2 is the wedge. Then the wedge move only to the right. So if I do this motion over here, this is the displacement of the rod, and this is the displacement of the wedge. You know that this is a straight down and this is the plane, so you can extend this down, and this is alpha. So this is then, if I draw 90 degrees over here, and extend this over here, you can see that this is 90, this is 90. So this is also alpha, and also this one over here. So tangent of alpha is opposite over adjacent. So I can write it like this. Y position of the rod minus the initial position of the rod is tangent of alpha x position of the rod minus the initial position of the rod. And now if you take two derivatives of this equation, this is a constant, the initial position is a constant, this is a constant, tangent of alpha is a constant, you get a1 in y equals tangent 8,2 in x. So when I put over here, the acceleration of the rod is only in the y-axis, and the acceleration of the wedge is only in the x-axis. Anytime you see a1, a2, it means the y and the x in each case. And this can be written like this. So this is my first equation, is the constraint equation. And that is the one that is hard to find. Again, the displacement is straight down for the rod, and the displacement of the wedge is straight to the right, as you can see from the figure over here. So now let's put the free body diagram for the rod, the free body diagram from the rod. You have wedge on rod, and you have M1G, and again this is alpha. So, and the free body diagram for the wedge, you have rod on wedge over here. This is wedge on rod. This is rod on wedge. And let's call this M prime, floor on wedge. So floor on wedge is straight up. Let's call it M prime. And M2G is straight down. So let's put the equations over here. I won't bother because I already showed you that the motion is only in the y-axis, so I only care about this over here, and I only care about this over here. So this is going to be positive, and this is going to be positive. So over here I have an N2 and 1, 2, I will just call it N. So I got N cosine of alpha minus M1G, and the acceleration is down. So make sure you put this negative because the rod is moving down, and I put this as positive. So A1 is the magnitude of the acceleration. So this is equation 2. And equation 3 is in this axis. Is just, again, as you can see over here, this is alpha, and n1 2 n2 1, they have the same axis, so this is alpha, and this equation is quite simple, is n sine of alpha is m2, a2 is positive because the wedge moves to the right. Yes, there is an equation for n prime in this axis, but you don't need it. I will put it over here. So n prime minus m2g minus n cosine of alpha. And you can see that that's 0 because the wedge doesn't move in the y-axis. So the normal force floor on wedge can be calculated using this if you know n. However, the problem is asking for the accelerations, but you could solve the problem. You could solve for the normal force acting on the wedge, and you could solve for the interaction wedge on rod on wedge. So we are going to focus on the accelerations because that's what is being asked. Okay, these are the equations, and I think the base idea is to modify 2 to move n1g to the other side. So that's is going to be n cosine of alpha m1 and then g minus a1. And now I will divide 3 by 4 because I will get tangent. I will get tangent on the left. So you have 3 and then over here I have ma2 so the normal 4 cancels. That's the reason I did it, but I get tangent of alpha and then I get a2 and this is m2 m1, which is this g minus a1, and now I will divide by a2, so I get g over a2 minus a1 over a2, and this is tangent, and then I only have an equation with a2, so I get tangent of alpha g over a2 minus tangent of alpha. And now I cross multiply. Move this to the other side. Divide by tangent. And remember that 1 over tangent is cotangent. So I get mu cotangent and tangent when I divide by tangent. So the acceleration 2 is, if I flip that, and this is the acceleration of the wedge that is to the right. Now it's super easy to find A1 because it's tangent times A2 times tangent. Then I divide by tangent. And 1 over tangent is cotangent, so A1 is now it's not being asked, but you could find the interaction rod on edge, wedge on rod using equation 3. And using this equation over here, you could even find the normal force floor on wedge, and then the problem is solved.